Welcome back. Today we'll talk about continuity. This goes with assignment number 5, section 2.3. At this point, I'd like to say that it's a very good idea to carefully read the opening 2 paragraphs of section 2.3. This gives a pretty good working idea of what continuity is all about. Unlike the definition of continuity in the text, I find it's helpful to break this definition down into 3 parts, as you will see below. So f is continuous at x equals c if and only if f of c exists, the limit at x equals c exists, and the limit at c is equal to f of c. The following 3 diagrams will help you understand specifically the conditions under which a function will fail to be continuous. Each of these functions fails to be continuous for a different reason based upon the previous definition. For example, the first graph that we're looking at fails to be continuous because f of c does not exist. The second graph function that we look at fails to be continuous because the limit as x approaches c of f of x does not exist. And the third graph is probably the most interesting because in this case this function is continuous at x equals c because the limit as x approaches c of f of x does not equal f of c. And when you're asked whether a function is continuous or not, and you decide that it's not continuous, there are only 3 possible reasons for why a function won't be continuous. Either it doesn't exist, the function doesn't exist at the point, the function fails to have a limit at the point, or the function does have a limit at the point, but that limit does not equal the value of the function at that point. Visually, if you have a graph of f of x and you're asked whether or not it's continuous, the idea here is to think about whether the graph is connected. In other words, can you draw this graph without lifting your pen from the paper? If you can, it's continuous. If you can't, then it's not continuous. When we're talking about different types of discontinuity, there are 3 kinds that we generally consider. A jump discontinuity will look something like this. An infinite discontinuity will behave like so. And the more interesting kind of oscillating discontinuity might look something like this. Previously, we talked about what it means for a function to be continuous at a particular point. We more often say that a function is simply continuous if and only if it is continuous at every single point in its domain. And that's a function which, as we said before, can be drawn without lifting your pencil up from the paper. We do have another theorem, a fairly important theorem that has to do with the composition of 2 functions. And it simply says this, that if f is continuous at x equals c, and g is continuous at f of c, then g of f of x is continuous at x equals c. And here is the statement of that theorem. Finally, we have a very important result that will continue to come up, and that's known as the intermediate value theorem. And what it says, again, is something that's very believable when you think about a continuous function. And I'll state it and then I'll write it. What it says is that if f is continuous on the closed interval a to b, then f must take on every single value between f of a and f of b. If f is continuous on the closed interval a to b, then f takes on every value between f of a and f of b. Another way to look at that is the following. If f is continuous on the interval a to b, and n is between f of a and f of b, then there exists at least one value c in the interval a comma b such that f of c is equal to n. That's a more interesting way of stating that same result. So that concludes today's work on continuity and assignment 5, and I'll see you next time.